Hello, everyone. Welcome to the binary half of the podcast for this week. I'm Spectre. With me is Z. We'll cover the Spot the Vuln challenge for this week, and then we'll get into some news and exploits. So, Z, I'll let you take that one away.
Yeah, so Spot the Vuln this week, a number of people got this in chat, actually, before we even started the stream yesterday. And this is kind of a classic issue, but oftentimes you'll see the, when iterating over a string in particular, so character array, you'll often see, you calculate the end just by taking the buffer position plus size of the actual buffer. That logic doesn't quite work when you have something that isn't a single byte in length. And this just comes down to pointer arithmetic in C. So what's going on in this one, or where the problem is in calculating that end pointer. And for those of you listening, effectively we've just got code allocates a buffer on the stack, has a pointer to it, has a pointer to what it presumes is the end by doing buff plus size of that buffer. Doing that plus size of the buffer, because size of is going to give you the bytes back. Adding to that then adding to a pointer is going to implicitly add multiplied by whatever the size of the thing it's pointing to. It's kind of does that implicit conversion, which means that end pointer is going to be whatever the size of an integer is, 4 bytes or whatever it is. That's going to be platform and compiler dependent, but basically this will point 4x or significantly beyond the actual end of the buffer, so that it iterates over it, going well beyond where it should, giving you kind of, in this case, a classic Stack Overflow.
Yeah. That said, this type of issue, I don't know how easily you could exploit it, because this is going to be a very large overflow. You're going to end up smashing a lot of stuff on the stack, but it's definitely a kind of bug that I've seen before, because size of just isn't super intuitive sometimes. It's easy to think that size of is returning the number of elements in an array, whereas to get the number of elements in the array, you have to do the size of divided by how big an item is in that array. So it's kind of easy to make that mistake if you're not thinking about it too much. So I have seen bugs that have been based on this type of issue before, for sure.
Oh yeah, it's
Um,
it's definitely been there. In terms of in terms of actually exploiting it, maybe. It's going to depend a lot on the actual function that it's within, because you are, in theory, assuming there's no stack protector, which should, by default, get placed in here with both Clang and GCC. Because of that allocated buffer on the stack, it should choose to protect it, so that's another limitation. But assuming you're actually there, you've got return address control of that function. So as long as you can get it to return relatively easily, even though you've corrupted everything else, you've still got a good chance at code execution there. Because it doesn't have a chance to start using that other data.
yeah, fair point. But yeah, pretty cool issue. So now that we have that out of the way, we'll move into some of our topics for this week. So we'll kick off with some news from Google's VRP. They've launched a new campaign running until January 31st of 2022, where they'll be paying $31,000 for Linux kernel privilege escalations of previously known bugs, and $50,000 for 0 days or new exploit techniques. It is worth noting this is not just standard vanilla Linux. This does require the exploit works in their container optimized OS, which is hardened in both attack surface, I believe, as well as exploitation primitives, which is a detail that I've seen left out in some discussions around this. Some of the tweets and stuff I've seen seem to indicate it's just Linux kernel, but it's not quite that easy. But yeah, so still pretty big news from Google here that they're paying out this much. This is built on top of their KCTF VRP from last year, which I think somehow escaped both of us. I know I wasn't aware. I don't remember, but I don't think you were aware of that either. Were you, Z?
Yeah, no, I was a little bit surprised actually to hear KCTF had a reward program for it. I mean, I think it's great and it makes sense, because that is utilizing, a lot of the same tech that's going to be used on Google Cloud itself. So it makes sense that they do have an offering there. But yeah, I just wasn't aware of it, and I figured some of the others listening might not be aware of either that, or might have an interest in some of the at least somewhat more kernel focused things instead of just going for Android. Like you said, there's a caveat on that, but um, yeah, it's a little bit more accessible.
Yeah, I mean it's pretty nice to see because with Linux kernel outside of Android, there aren't a ton of options really for a submission if you want like if you're expecting payment, right? Like you've had like ZDI and whatnot, but ZDI is a little bit of a pain to work with, and their payouts are not this high. They don't pay like $30,000 for basically exploits for n days. Like that's pretty crazy, and they certainly don't pay $50,000 for 0 days. So, yeah, I mean this is a really good option to look at if you're looking for a target that's interesting in binary. Linux kernel is pretty much the apex of interesting outside of maybe browsers. So it's a really good target to look at. And yeah, I mean the incentives here are pretty good. So
I mean, on binary, you do also have Windows stuff. Just since you
who
went and
wants to
said
do
it's the
Windows?
apex of it, I mean, Windows is pretty popular. I know we both kind of are more in the Unix styled world, I guess, but yeah, Windows is there too.
So
Like,
that's fair to point out. What I was thinking in my head and I didn't say out loud, just to clarify, is I meant in terms of like open source software where it's relatively easy to get into Vuln research on it. With Windows, you're right. There are bounty programs for that too, and it is certainly interesting code. But there is kind of that barrier to entry where you have to have reversed code or operate on leaked code or whatever. Like it's not as easy to just jump in and start doing Vuln research. So yeah, that's what I was kind of had the stipulation in my head, like in open source software terms.
yeah,
But
and in
yeah, that's
open
fair to call out too.
source, well, I mean, open source in general just makes it a bit easier to get started. Although on that, like you said, you do have the browser sources also. Chromium is open source, which is frankly the main target when it comes to browser exploitation. I mean, technically, Mozilla does have a bounty program, but it's kind of just blown out the water by Google and Chromium.
I have kind of made the joke before with browsers that it's almost worse to read the source code. You're probably better off just reading the disassembly because it's probably easier to follow. That's just like joking on the complexity of browser engines because being frank, a browser is far more complex than something like the Linux kernel. So, yeah, I mean, the Linux kernel is it's a relatively interesting target, but it's also a lot easier to get into than browsers. So,
Yeah, there's a lot more documentation, obviously being open source, but just in general, like you can find out a lot more about operating system internals and those core concepts, I think, easier than browser. That said, I haven't done a ton of browser work, so I haven't tried to ramp up on a browser either. Maybe I'm mistaken on that, but yeah, I'd agree.
yeah, I don't want to go too deep into it, but that is like a good point to bring up because that's part of the problem is like browsers are a lot more cutting edge. You have a lot more like new features and new subsystems being rolled out, lots of movement in the code. Whereas the Linux kernel's, I mean, it's seeing weekly like a lot of patches and stuff, but it's not changing in the core nearly as much as like a browser is from what I've seen. So
Yeah, I mean that's starting to change actually. Linux, if not in terms of like I still feel like optimizations, everything like browsers are crazy. I'll leave it at that. That said, Linux especially last year, couple years, they have moved to a much more frequent release cycle, like since 5.0. Because now they're oh no, they put out several minor versions just in the last year. Like they've been updating what feels like they're putting out releases a lot more frequently, and the development process has been speeding up compared with
yeah,
older versions.
yeah, I think even recently, like as recently as the past week, there was a new Linux kernel version announced that has like kernel support for Samba and stuff like that, which that might be interesting to look at if you're looking at doing this VRP because typically the newer attack surfaces are, you know, buggier because they haven't been thoroughly tested and hit as much. Um, so I guess I'll give that as a quick shout out or quick tip if anybody's looking to do it. But yeah, I mean, overall, just wanted to shout this out because it's a cool target, and like these payouts are very good. I mean, it's from Google, so you kind of expect that. Google's always been really good with their payouts, but I mean, yeah, this is the best VRP that I've seen, and is like between the last couple ones we've covered. So
Yeah.
yeah. All right, so we'll move into some of our hard vulnerabilities for the episode here. So for our first vuln topic, we have a race condition in Android's NFC stack, which leads to type confusion. This was reported by Ned Williamson at Google Project Zero. As the report is a bug tracker report, it's not like a write-up or whatever. The fine details are a little bit elusive if you're not familiar with the code base. So I am going to make some assumptions here. But the idea here is the NFC stack uses objects called TCBs, which I believe stands for task control blocks. I couldn't really confirm that because the documentation sucks on certain things for Android. So yeah, I believe they're task control blocks. That's how I'll refer to them. But anyway, in NFC, you can have like tasks or packets that come through. And the NFC specification supports a variety of formats and protocols for different types of NFC tags. Because of that, in these control blocks, the tag type has to be tracked. And the other thing is the control blocks also have an auxiliary data buffer for storing timer information, because you can have tasks that have like a timer that fires after a timeout or whatever. And any data that it needs will be stored in that buffer, basically. The problem is when a tag is deactivated and another tag is activated in the NFC controller, the tag type on that control block gets reset, which in turn clears that tag specific area of the control block used for timer data, which then gets overwritten by whatever the new tag activation does. The problem, though, is when that happens, there might still be timers ticking and waiting to fire on that control block, and those timers don't get canceled when the tag gets changed. So if a tag change goes through and a timer event is handled after that change, there's a race where a type confusion can occur. The tag change can overwrite timer data. Then when the timer event fires, it's now operating on corrupted data due to the type confusion between the different tags. So in the POC case here, they transitioned between a I93 tag type to the T3T tag type, which I'm not familiar enough with NFC to really talk about the differences between those two specifications, but basically when an I93 inventory request is sent, it causes a timer for detecting a timeout to fire. Then the NFC controller causes the I93 deactivation and the T3T activation. And then that T3T activation will corrupt the timer struct, timer fires, and a seg fault happens because of the data corruption. So yeah, kind of a weird issue. I mean, it's a type confusion, which I do like to cover because they are typically more interesting bugs than, let's say, like an integer overflow or whatever. Um, Again, one of those bugs where it requires a little bit of understanding about what's going on in the code and like how these different tag types can be switched out. So, I mean, kind of a cool bug. Unfortunately, we don't have a ton of information about it though, or how it can be exploited, because this is just like a bug tracker report. But still, wanted to call it out because I think it's an interesting bug.
Yeah, I mean, I don't really have much to add to that either. A little bit interesting, just was the fact that this was found through fuzzing, which makes sense. Like, this is definitely a bug that feels like a fuzzing type of bug. Um, but a lot of Project Zero posts that we do end up covering are through source review, or
Yeah,
through having
very
read the
much.
source. So this one, it did catch my eye here that the methodology on this one was fuzzing. Not totally uncommon, but infrequent enough that it stood out.
Yeah, like you said, it's a bit of a rarity. So
Yeah, a
yeah,
rarity that a fuzzer finds bugs, right?
well, rarity that
No, I get what
P0
you mean.
releases a bug from fuzzers, but yeah,
Yeah.
um, yeah, and like you said, it kind of makes sense because this bug does seem like it would be pretty easily fuzzable as long as you like set up the harness to be aware of how NFC worked. So yeah. Next, we have a somewhat complex privilege escalation in PHP-FPM, which is quite commonly used by Nginx and sometimes Apache and other stuff. This is from Ambionic Security. Because it involves some of the lower level details of how FPM works, They do go into quite a bit of background on the architecture and some of the important data structures that are relevant to the vulnerability. But yeah, Z, I'll let you take this one away, and then we'll comment on it after.
Yeah, so like I said, this one has a lot of background, and there are going to be some points that I skip over if you want, like, all of the details on how this works. Because what they're talking about here is a bug where you already have at least arbitrary read and write inside of a fast CGI process manager worker. Um, so this is used as a privilege escalation. It would not be the first stage. You do need to already have kind of broken out of that PHP sandbox and have that sort of situation going on. That said, and because of that, this ends up being a attack from a worker to the root process. So what kind of matters here in this bug, and the very quick background is within FPM, it has this concept of what it's calling scoreboards. And the scoreboards, that's where all of the workers will have their own scoreboard and they'll track various statistics, like what script they're executing, or if they're even working, or if they're idle. And then FPM itself, in the root process, it has its own kind of collation of all the scoreboards. It has an array of pointers to all of the child scoreboards, and these all exist inside of just a single shared region of memory. So that's shared with the root process and with all of the workers. So a worker could mess with the scoreboard of another worker by just writing to it writing to its shared memory. But what's actually important on this attack is the worker can also mess with that the FPM. It's the root process's scoreboard itself. So it can mess with the pointers that FPM has that are supposed to point to where all of the workers' scoreboards are. So effectively, that's kind of the starting point, or the starting corruption here is a worker can control the pointer that the root process will dereference. So then, the article kind of goes into asking, well, what actually uses this array that you can get control over? And that ends up being, or at least what they focus in on. I would imagine there might be more areas that actually use this information, but what they focus in on is the free and the creation or allocation of scoreboard. So that happens, a new worker gets, so say a worker dies, crashes, something like that, it will free that worker. And when it does that, of course, it goes in there, gets the index, gets the pointer, goes into it, checks like, is its used field actually indicating that's not used? Or since it's freeing it, make sure that was used. If it was used, it's going to memset the entire structure as 0. Zero it all out, then allocates a new one, checks the used field again, make sure that it's 0 now, just ran a memset 0 on it, so it should be. And if it is 0, sets it to 1, marking that it's actually in use, and it gives it away. So those actually describe the two primitives that they have from this vulnerability of sorts. I do say of sorts because it's kind of a case of you have a hardened exterior and a what feels like a fairly soft interior. Anyway, so those two primitives I talked about are the mem setting that will clear 1,168 bytes, or a very significant chunk of memory. And the second primitive so that happens in the free. If used is a value greater than 0, you get that clear. And if it's not, it just skips that mem set. And when it goes to allocate, when it checks that use value, it'll check if that's a 0, and if it is, sets it to 1. That's the other primitive that they use more during this, is that ability to change a 0 in the root process memory to a 1. And these are 1 byte writes. 1 byte 0 to a 1 byte 1. So that does kind of let them tamper with bytes in the middle of values, rather than being like 4 4 bytes is 0 or 8 bytes or whatever the word size is. I will also note, because this does play a point a little bit later, that when it comes to ASLR, it's not a huge issue because all of the workers are forked from that parent root process, which means that the memory mapping and such will stay consistent, and they'll know, or all of the children can know quite a bit about the parent setup. So it doesn't really have much of an impact in this case. So anyway, so you've got those two primitives. And the way they end up targeting these two or using them is that 0 to 1 is useful for changing the feature sets. So you can have something that's by default disabled and they can turn it on. So what they end up doing is turning on this catch workers output. By default, this is off on the default install, and that when it's off, set to 0. When it's on, set it to 1. So by turning that on, what that gives them is the ability to control some of the data in the root heap. Because what happens with that catch worker output, effectively the functions or the feature is just saying like take all of the output that all these workers have and actually log it, write it into the FPM log. And before it actually writes out to the file, it will buffer it until it gets a new line and then write it. While it's getting buffered, that's its chance to control data that exists inside of the heap. And this sits inside of, or part of this for standard error specifically, sits inside of a zlog underscore stream structure. Every process gets allocated this structure, or every worker gets allocated this, but it's not actually initialized until something gets written out. Anyway, so you're able to use that 0 to 1 primitive to corrupt some of the data inside of that stream structure, which is it'll track kind of the size of the backing buffer. So when it does actually allocate data to it, you can corrupt the size of it or how big it thinks the existing buffer is, and you can corrupt the length, which is the number of bytes that have already been written to it. So that's kind of creating this heap overflow situation where basically think it has more room to write than it actually does, and you can overflow into the next items on the heap. A little bit of heap feng shui, coercing it so that you have two stream structures next to each other. And they do go into more detail about doing this and controlling kind of the worker process quite a bit more to make this a fairly stable exploit also. But they're able to set it up into that situation where they can overwrite into another zlog stream. And so what they get there is they can replace the pointer to that buffer of the second worker. And by replacing that pointer, anytime that second worker, the corrupted worker, anytime that one writes to standard error, it will basically be giving them an arbitrary write because they control the pointer where it's actually writing to. And then from that point, with an arbitrary write in the root process, it can overwrite any of the function pointers. And again, because of not really needing to worry too much about ASLR here, it's fairly easy to get the root code execution from that point. Like I said, I've skipped over a number of details. This is a fairly detailed write-up. Part of it felt like they included almost too much information, but there's a lot of background that, like, if you were interested specifically in PHP engine and this type of exploitation, there's a lot of background here that I think would be useful. But in just trying to, like, get to the point, when I was trying to summarize it, there's a lot to kind of understand here. It's not just a really trivial exploit to understand, but they give a lot of information, more or less explain everything you need.
This is another good example of chaining corruption logic to get better and better primitives. Because, like, what you were saying there was they start out with this set 0 to 1 primitive, which is very limited, obviously. Now, usually that can be taken advantage of in most targets because being able to change a single byte or a few bits will eventually get you to somewhere where you can do something useful. But you're kind of going from that set 0 to 1 to then causing the heap overflow to then getting control over a pointer to then get arbitrary right. There's like 3 or 4 steps before you actually get to you know the end game primitives, as I like to call them. So this is just a really good example of what some modern chains look like, with the amount of steps you have to go through to take a relatively minor corruption primitive and turn that into something useful to you.
Yeah,
So
I mean, you're basically playing Legos with the software in a sense.
yeah,
You've got that one, well, the two primitives, and you're keep reusing those little blocks to create something more and more useful.
there's a few other things that I thought I would point out here. For one, the main cause of this issue is the fact that the main scoreboard is in shared memory, right? And that's kind of interesting because obviously with the way that PHP-FPM is architected with this idea of like a manager or root process and workers, you have to have IPC. And because it's for fast CGI, that IPC, like I'm guessing the reason they went with shared memory here is because it's the most performant IPC you can have. There's nothing faster than shared memory. Um, but you know, managing shared memory is very difficult. You kind of you have a trade-off there. Like you get the added performance, but it's, doing access control and all that kind of stuff, it's way harder to do on shared memory. You kind of have to build on top of it. So this is just kind of showing how, that trade-off can come back to bite you because just shared memory is so hard to work with. And it's a good area to look for vulnerabilities. So I thought I'd
Yeah,
point
I
that out
mean,
because it's not often you see shared memory like that in real world, or not in most of the topics that we cover anyway.
yeah, I don't think we have talked obviously about shared memory things. A lot of times, what we end up talking about when it comes to shared memory are more of like the double fetch style vulnerabilities. And for what it's worth, to patch this one, what they did was they just removed since I talked about the main scoreboard there having an array of pointers, now it's just an array of the structures itself. So no pointers to corrupt. No pointers, you can't get that dereference anymore.
Yeah, it's just a large auxiliary buffer that contains all the objects side
Yeah.
by side. Yeah, makes sense. But yeah, I mean this issue and the way they exploited it had some real CTF like vibes to it. Just like that weird restriction of how your primitives are. Um, so yeah, I mean that was something I found kind of fun with the post. But yeah, like you said, it's a very complex attack. It's not something where it's like, we just had a simple overflow and then we found something that worked. This was like a multi-step process, and it does, like, if you want to fully appreciate it, you do need to read some of the background and understand like the different features of the program that they're exploiting to get to that stage. So there's a lot of reading there, but like Z said, if you're interested in PHP FPM, this it's probably a good reference for all the background information that it has and whatnot. All right, so finally we have another Vuln topic before we get into shoutouts, which is CallbackHell, a named Win32k Vuln. Here we have an exploit repo from Oliver Liak. I don't know if I said that right. I probably didn't. Sorry about that. But yeah, it's his exploit repo that talks about the bug, though Kaspersky also did a write-up on this issue, so you can refer to that if you wanted a more detailed write-up, because this is mostly talking about how he exploited it.
Yeah, I
Whereas
mean,
Kaspersky goes a little bit deeper into the root cause analysis side of things.
Kaspersky's felt like it was also kind of short. Um,
It was shorter than I expected for sure. Yeah.
yeah, like I mean, it was still I actually referenced it more. Although I guess they do also have the secure list post, which I'll make sure we have the link to that one in the notes. But obviously Kaspersky being more of the antivirus, they were very focused on the fact this was in the wild, or this was something that they actually saw being used. And that was more of the focus, although they do, of course, talk about the actual vulnerability. Anyway, let's get back to that.
Well, more interestingly, just where you were saying it's being used, not only is it just being used against companies or whatever, it's being used against military and defense contractors. So this is a this is being used in a very impactful way too. But yeah, we can go ahead and get back to the vulnerability now. So yeah, I mean, this kind of had multiple names. Kaspersky named it Mystery Snail. Obviously, here in the repo, it's called CallbackHell. As the name suggests, the root of the issue here is the fact that Win32k allows users to specify user mode callbacks for drivers, and if that isn't properly accounted for by the driver, the callback can trigger some destructive action on the original device context, which can cause something like a UAF later on. In this specific case, it's in the nt-gdi reset DC function. GDI, yet again, same as the last time we talked about this issue, because we talked about a very similar issue to this in a podcast episode before, though I forgot to get the episode number because I meant to do that.
Yeah,
I don't know if you have it saved.
I don't have it, unfortunately. We have
Okay.
covered GDI issues. I think it was before the break we covered a couple of them almost back to back.
Yeah, I think it was not too long before the break. You're right. But unfortunately, I don't have the exact episode number on hand. But yeah, I mean, it's an issue that's cropped up before. So the problem here is the callback can issue. So when you use this nt-gdi reset DC function or syscall, you can choose to pass a handler or not. And in the callback, if you issue another reset DC syscall while the first one is executing in this callback, and that second syscall is invoked without a handler, it will then destroy and create a new DC context, which then triggers a problem when the first reset DC syscall returns from the handler and operates on that UAF DC. So it's kind of this weird problem where what happens if you call the syscall while it's already been called somewhere else, right? And it's in that handler. When you're giving the user control over the flow of a syscall like that, it's very dangerous, and it's very easy to have a bug like this. So yeah, I mean, pretty straightforward issue when you understand how Windows syscalls allow you to pass these callbacks. The README talks about how they exploited this and walks through some of the steps, which involved utilizing an available printer and installing a custom user mode callback entry into its callback table, and then creating a device context for that printer. They then install this malicious callback that'll trigger the UAF using the steps I described earlier. And they use color palettes as a reallocation primitive to smash a function pointer in the UAF object that gets called after the user mode handler is finished. And code execution is achieved pretty easily here. It's not like the PHP-FPM bug where they had to chain a bunch of corruption primitives. This one, it's pretty much you just, as soon as you reallocate, there's a function pointer that gets called, and you can just get a hijack there. They point out that KASLR isn't really an issue here because it's Windows, and as long as you can use the NT-query system information and enum device drivers, which is available in medium integrity, you can get kernel pointers and defeat KSLR pretty easily. The way they abuse the code execution was somewhat interesting, though, I thought, because it is a previously documented trick, but it's not really one that I'd seen before. Basically, they abuse this internal function called RTL set all bits, which is used for changing bits in a bitmap header, and they set the argument to the current process token. So they're kind of abusing a type confusion there, to get RTL set all bits to smash the process token to enable all privileges on it, which, I mean, the endgame for Windows exploits in the Windows kernel, it often is to attack that process token. That is like the easiest privilege escalation primitive to go for. But like using the function used for like setting bitmap headers to do it was kind of interesting, I thought. That said, there was a lot of other options they could have gone with there. That was just the one that they used, but yeah, I thought that was kind of cool.
Yeah, I mean, like I said, it's one that's already been known about, so I guess they linked to another write up about that. On a whole, like I like, just the idea you have that callback, and you're basically calling the callback inside the callback, callback inception. It's a fun little attack. We've seen a few similar things before.
But only in Windows. I've
Well,
not seen a bug like this in another product. But I mean,
I,
there might be some others out there, but Windows seems kind of unique in the amount of power that it gives to people
so
in
we've
user land
seen
over kernel context.
Yes, when you're specifically speaking about LPE, so for this privilege escalation, yeah, we've only really seen that with Windows. That said, this is also very similar to something like the PDF exploits that we've talked about.
That's true.
Oh,
That's
like
fair.
where you have the callback there. I mean, that does get a little bit more JavaScript, which is nice and callback friendly and callback heavy. Sorry. Um, but yeah, I mean, I don't know. It's a fun thing to think about because again, a lot of people, your thing, you have the callback. It's going to do whatever you need, but it's easy to forget about the fact that you can potentially end up tampering with the data itself that it's expecting to be stable.
Yeah. Yeah. I mean, most of the time when you see these kinds of callback bugs, it's usually in the context of a browser. Like we covered one in, I think, Chrome like a week or two ago that was in a callback. So, yeah, I mean, I should have clarified what I was saying there. In the context of a kernel, I have only seen this in Windows. Um,
Yeah,
and
I
yeah,
can't
it is
think
a
of
little bit
anywhere
weird
in
how
Linux
Windows.
that would like you kind of do this. I mean, maybe it is there. I nothing comes to mind though.
Yeah, Windows is a little unique when it comes to exposing capabilities. Um, and that's just because of how Win32k is architected and the legacy like code debt that's inherited because of Windows's or Microsoft's philosophy when it comes to Windows with trying to keep that legacy support and whatnot. So that's what crops up these kind of weird issues that you might not see in other products in the same category. Yeah, so that's most of our topics. We do have a shout out. This is a cool write up from CTS, who we've had on the podcast before, actually, which some of our veteran viewers might remember. Um, the write up here details a CTF challenge he wrote that involved a race condition on a lockless ring buffer implementation, but one that only exists on ARM and not on x86. It's a really interesting and cool case study because like lockless buffers and lockless data management is already like an intricate and kind of complex subject. Um, and here it involves how x86 and ARM differ when it comes to like CPU optimizations and out of order execution. The too long didn't read of that is that ARM will do more when it comes to memory reordering than x86 will because ARM has a weaker memory model. So where x86 will only reorder older stores with newer loads, otherwise known as store load reordering, ARM will reorder any memory operations,
And
excluding data
just
dependencies.
to
So
jump in really quickly, to clarify, I guess, when it comes to memory reordering, what we're talking about are the memory access, the read, the loads, all of that, not actual memory being reordered. I know that's not what you were saying, Spectre, but at the same time, just saying memory reordering, I could understand a listener thinking that ARM is, just randomly, oh, you
shuffling
want to,
memory.
yeah, exactly. So
Yeah.
I did want to clarify that point. It'll reorder the execution of stores and loads to memory or from memory. And it'll do that across more boundaries than what x86 would, giving less kind of memory guarantees than you might be used to.
Yeah, that's a good clarification. Um, so yeah, because of that difference where ARM is a little bit more generous with how it'll do the memory reordering, um, assumptions that are made based on the x86 memory model are broken. Now, obviously, there is a lot more nuance to that. The post goes into detail on the code and exactly how this can be exploited to eventually get a race UAF or double free, which is then taken to like an arbitrary read and write. This section is also worth a read on its own, even if you're not that interested in the bug. Although I will say, like, the bug was a very cool read, um, because it like the section where it talks about exploitation, it talks about glibc and getting around the T-cache mitigations, which we've also talked about a few times recently. But um, yeah, I mean that information on its own could also be useful to you, even if you're not interested in attacking an ARM platform or whatever. But yeah, just a really solid read. And well detailed with like good diagrams and stuff. But we wanted to shout it out because it would be difficult to do this post justice as a full topic, because like I said, it involves a lot of nuances with lockless programming, and you kind of need the visualization that the graphs provide and whatnot to understand what's going on, it'd be really hard to cover it well in an audio only context. So that's kind of why we just want to leave it as a shout out. But I do really recommend that, anyone who is interested in like lockless programming and these weird types of bugs when it comes to CPU optimizations, this is a really cool post.
Yeah, solid post, hard for us to actually cover. And technically it's a CTF, not a real world vulnerability, so we can skip it on that note, but did still want to give it that shout out.
For sure. But yeah, so that's where we're going to end the show for this week.
Before
Thank you to
we
everyone who
end,
tuned in. Oh, do you
I
have something
actually
else?
I do have one more thing, and that is a question out of chat from Detox Mango. It's not
Okay.
like mangoes, but he asked the question that gets at maybe an interesting point. How many bugs do the best of the best find? My initial thought is, of course, fuzzing. You can find thousands of bugs, in a day, in an hour, even. You could just have the fuzzer go crazy. It'll find plenty of bugs. But then it takes a lot more work to go from a bug or a vulnerability to your actual exploit. And I brought that up in chat, and the clarification on that was RC, or zero DM bugs. Which, fair question, I think. Like, somebody who's, say, wanting to sell zero DM, how many bugs that they find, and it does vary. I mean, I don't think there's any sort of metric that we can say is how many do the best of the best. Like, one, I think the amount of bugs it's not a very good metric of anything. One, for fuzzing, two, source review, but also kind of the power of different targets. You might be more likely to find a bug in antivirus bugs. Zero DM, I think, pays like $10,000 for an antivirus LP, versus an iOS. Like, there's a very significant difference there, in terms of how many bugs one you're going to find and the effort need to actually find them.
I
Um,
mean, the problem with the question is it's highly target specific.
yeah,
And not even just down to the product type, like even the type of subsystem you're looking at. Like you could be looking at, let's say, iOS, and if you're looking at an area that's already been hammered, like the damn, I can't remember the name of the subsystem. But like if you've hit a subsystem that's recently been targeted and it's been targeted for years, you're probably not going to find as many bugs as if you look at a new subsystem. So there's a lot of context and nuance there where it's not something you can answer broadly or like as a general,
yeah.
this is the
There's
answer.
no general answer, but I did actually want to bring that up as the fact that you can have bad luck. Like, somebody who's good can still spend quite a bit of time and not actually have a finding. The more familiar you are with code base, generally speaking, there's kind of this ramp up period of potentially on harder targets, several months of not finding anything, but then you might find like 3 bugs in one day or 5 bugs in a day. I think there was maybe it was Project Zero, I was going to say it might have been the Microsoft team, but I don't think so. Where they mentioned like we had somebody working on this and they had like no findings for 3 months, and then they had several bugs in one day. It's very much a gamble on that, and I don't think that's a good metric on the best of the best, anyhow. But then, what would be a good metric? Like, how would you measure that skill level? And I mean, I don't have an answer to that. So I'm raising that just kind of as what would you measure? I mean, you can measure bugs found, sure. You can measure the quality of the exploits, but that depends on the primitives you get from the bug itself. Creativity maybe, but that's not really a measurable thing. You can't really measure creativity. Consistent output is, maybe not really a measure, but at least a signal. I think the question gets at that interest point of how do you actually measure skill in this area? And
Yeah, I mean, where
it's
there's a lot of luck involved, it's why I'm not a fan of, because I know some companies for like security engineer positions, they'll have kind of like a bug quota where it's like you're kind of expected to hit this certain number of bugs within like a year period or whatever, and if you don't, then you're kind of, put on like a flag for review or whatever, which like that's one reason that I not really comfortable with the concept of that because, like, honestly, there's a lot of luck involved in Vuln research on modern targets. It's their skill certainly. It's not entirely luck based, but um, especially with things like fuzzing, it's it's time and luck. So
Yeah, I mean it's one of those things because of that it's so easy to fall into that trap of thinking that you're no good because you have no findings and comparing yourself to somebody else who's had plenty of findings, and it's always circumstantial. It's I think people can have quite a bit of skill and just have some bad luck at a time. Um yeah, I mean, I thought it got to an interesting question. I do kind of agree with you. The question itself maybe isn't the best, but it's reaching or pointing towards, I think, kind of that interesting point on how do you even measure skill to begin with.
So we shout this out quite a lot, but that is because it's a really good talk. But the Layman's Guide to Zero Day Engineering actually talks about this exact topic. I think it's toward the like earlier part, like maybe like 10 minutes in. They talk about the process behind finding and exploiting 0 days and like the timelines. So I like in my head I kind of remember where they had like calendars being shown where it can take like weeks, or you can find a bug in like days and then it zooms out, or it could be weeks, or it could be months, or even like up to a year, or whatever they were saying. Like it's really dependent on multiple factors, including like the target you're looking at, how many people you have looking at it, where you're looking, um, the state of the development process. Like there's just a lot of nuances involved there. But yeah, I mean, from like the question that you asked, I think this talk would be very interesting to you. So I did want to link it. And yeah, I mean, I just like to recommend it in general because it's an awesome talk. It's an inspiring talk, honestly. So
Yeah, it's a good talk. I mean, especially on their process side.
yeah. But yeah, with that answered, here's where we're gonna end the show for the week. Thank you to everyone who tuned in. The VOD will be up on Twitch immediately or on YouTube at 6 p.m. Eastern tomorrow. We also have previous podcasts up on Spotify, Apple Podcasts, and more links on Anchor. For alerts of when we're going live, and to join the community, follow our Twitter and join our Discord. Links for those are down below or in the chat. We'll be back next Monday at 3 p.m. Eastern, 12 p.m. Pacific for bounty stuff, and next Tuesday for 7 p.m. Eastern, 4 p.m. Pacific for binary stuff. And we'll see you all then. Take care.